Welcome back, guys. Today we're talking about acids and bases, two of our favorite things. You already should know that acids are compounds that start with hydrogen, followed by an anion. An anion could be either a nonmetal or a polyatomic. Either one works. They are special. We're going to be working with them in great detail in a much later unit, but today we're just going to learn how to write their formulas and how to name them. Just like we were doing with ionic compounds, when you're working with acids, you have to make sure the charges of the compound balance out to zero, because electrons are still being transferred just like in ionic compounds. To demonstrate this, we're going to look at hydrogen and nitrogen, but it should look similar just because, it's the exact same process as we were doing with ionic. So we're going to start with our two elements. Here we've got hydrogen and nitrogen. Hydrogen has an ionic charge of +1, and nitrogen has a charge of -3. Those are definitely not balanced. So what you need to do is add some more hydrogen to make it balanced, because right now hydrogen is +1, nitrogen's -3. There's a lot more negative than there is positive. So I'm going to do a little scratch work over here on the side. If you have hydrogen with the +1, nitrogen with the -3, you have to add 2 more hydrogens in order to balance out to be a +3 total to match out your -3, so that everything cancels and the total charge of the compound is 0. That means the formula is going to look like H3, because you had to use 3 hydrogens, with an N, because you just used 1 nitrogen. Alternatively, you can use that lovely crisscross method, where you just take those ionic charges and cross them down. So the 3 that's with nitrogen comes down to the hydrogen, the 1s with hydrogen comes over to the nitrogen. Easy peasy lemon squeezy. This looks just like ionic bonding. Same principle, same process, works out exactly the same, should look familiar. So down here, I'm going to let you guys try to figure out all of these combinations. Some of them do involve polyatomic ions, and I'm going to do one of those for you real quick, just so you can see what it looks like. Let's do number 2 with the polyatomic ion. Hydrogen and sulfate. So hydrogen is H with a +1 charge. And sulfate, you got to go look up on your polyatomic ions list, which I'm going to do here real quick to make sure I don't mess it up. Sulfate is SO4 with a -2 charge. So you're going to have to balance those charges out. The 2 is going to go over to hydrogen, and sulfate's going to be just 1 with SO4. Works the same way, same process as before. All right, you try to do the rest of these examples. We'll see if you get them right. All right, there's the answers for you. Check through them. Be sure you got everything right. If you feel super lost, missed all of them, have no idea what you did wrong, please contact your teacher or come to office hours to figure it out, or rewind this video and watch it again. But now I'm going to move on to a little bit of vocabulary here. That vocabulary is binary acids versus oxyacids. So binary means 2. Binary acids are one that only have 2 elements. Binary is 2, so that's going to be a hydrogen plus a non-metal. Oxyacids, on the other hand, are made from hydrogen and a polyatomic ion. And all of the polyatomic ions that we're going to be using for acids contain oxygen, so that's why we call it an oxyacid. Oxyacid for containing oxygen. We're going to look at the following list of acids, not of elements, of acids, and decide if each one is binary or an oxyacid. Let's look at number 1. HCl, that just has hydrogen and chlorine, so it is a binary acid. Next up, hydrogen and PO4, which contains oxygen and is a polyatomic ion, that must be oxyacid. I'm going to pause it. You go through, try to answer all the rest of them, see if you get them right. And there you have it. Hopefully you got those right. Again, if you didn't, pause, try to figure out what you're doing wrong. This is going to be a really, really important concept for naming, is being able to differentiate between binary and oxyacids. All right, we're going to move into naming acids. Naming acids gets a little bit complicated because there's a different set of rules depending on if it's a binary acid or an oxyacid. Let's look at binary acids first. For binary acids, we're going to write the prefix hydro. We're going to put that at the beginning of the compound. Let's look at an example as we go. Let's see. We're going to look at number 1 here, HCl. That is a binary acid because it's only got 2 elements. So to name that, we're going to write the prefix hydro. Just write it right there on the line, hydro. And then we're going to write the name of the nonmetal. The nonmetal is Cl. So we're going to write chlorine, but we change the ending to IC. So chlorine will become chloric, hydrochloric. And step 3 is write the word acid at the end. This is hydrochloric acid. However, there's an entirely other set of rules when it's an oxyacid instead of a binary acid. So let's look at number 2 for that. I'll highlight it in green as well. Okay, so for oxyacids, the first thing you do is write the polyatomic ion, but you have to change the ending according to some rules. So we look at polyatomic ion here, PO4. That is phosphate. Now the rules here say if the original name ends in ate, you change the ending to ic. If it ends in ite, you change it to us, or OUS. This one is phosphate, so we change to ic, phosphic. However, we change that a little bit differently. This one is actually phosphoric. That's probably kind of a bad example, but it is an exception. Phosphate comes from phosphorus, which makes it change to phosphoric. It's a little bit different. However, you'll note this also happens when we get to something that's sulfate or sulfite. It'll become sulfuric or sulfurous. And then after you write that, you put acid. Let's do another example that doesn't have an exception in it. Let's look at number 3. Number 3 is HNO3. That is an oxyacid because it's got more than 2 elements in it. And we'll do the same rules. We write the name of the polyatomic ion, but change the ending. This polyatomic ion, NO3, is nitrate. 8 is going to turn to ic. So nitrate will become nitric. And then we write the word acid on the end. So that one's a little bit more complicated, and you've got to remember this 8 to ic and ite to OUS. The way that I help my class remember it is that we say we ate something icky. Ate something icky. That helps me remember it. And then you just have to know that the other one is ite, goes to OUS, because those are the other 2 things. But ate something icky, and then ite goes to OUS. Go ahead and pause, try the rest of these examples, and I'll throw up the answers in a second. Here are the answers. Hopefully you got them right. If you didn't, feel free to rewind and watch the explanations again. And if that doesn't help, you can always email your teacher or come to office hours. We would love to see your faces. All right, we're going to move on down to using the formulas to write names. Or sorry, that's backwards from what I meant. Using the names to write formulas. It's basically doing everything we just did backwards because we were using formulas to write names. Now we're going to go names to formulas. The first thing you got to do is figure out if it's a binary acid or an oxyacid, same as we did last time. And the way that you tell is if it has this hydro prefix. Because if it's got a hydro prefix, that means it's binary. If it doesn't have a hydro prefix, that means it is an oxyacid. So that's how we can tell. Real quick, we're going to sort these examples down here into oxy and binary acids. So you can tell if it's binary by if it has a hydro prefix. This first one, hydrosulfuric acid, does have the prefix. So I'm going to highlight that as binary. Sulfuric acid, on the other hand, does not have hydro, so it is an oxyacid. Same thing with sulfurous. Doesn't have the hydro prefix, so it is oxyacid. Now, binary acids are really easy. They're just hydrogen plus some nonmetal. And the nonmetal is the other half of the word. So we put H for hydrogen, and sulfuric comes from sulfur, which is S. Now, the thing that people forget to do, that you need to always remember, is that you have to balance the charges. Anytime electrons are being transferred, you have to balance charges. The charge on hydrogen here is a +1. Sorry, that's hard to read. And then sulfur is a -2. Those are not balanced, so we can do the crisscross method to get H2S. That's the chemical formula for hydrosulfuric acid. Now, when you move on to oxyacids, things get a little bit more complex because you have the weird ending rules. So let's look at sulfuric acid. Sulfuric is going to tell us what polyatomic ion, because it's an oxyacid, what polyatomic ion this comes from. And that ending, ic, is what's going to give it away. We know that ic came from a polyatomic ion ending in ate, A-T-E. So sulfuric had to come from the polyatomic ion sulfate, A-T-E. So that chemical formula is going to be made up of hydrogen, which is a +1, and sulfate, which is SO4 with a 2 negative. Those charges are not balanced, so you got to crisscross them to get H2SO4. And that is our lovely sulfuric acid. On the other hand, sulfurous, OUS, had to come from a polyatomic ending in ite. So sulfurous is going to become sulfite, which is different than sulfate. So you still got hydrogen, because acids always start with hydrogen, which is a +1. And sulfite, which is SO3, 2 negative. Charges aren't balanced, so you got to crisscross them to get H2SO3. So note that all of these names sound pretty similar. You've got hydrosulfuric, regular sulfuric, and sulfurous acid. All of them sound similar, all of them are acids, and their chemical formulas even look a little bit similar. But they are different, and you have to be able to use the rules to find the correct formula, not just one that's close, the correct formula. So always remember these two little rules. You ate something icky, and then ite goes with OUS. And in the end, don't forget to balance out your charges. So that is it for acids, and I say that's it. That was a lot of stuff, and we're still got a little bit to go. We're going to do bases really quick, but bases are way less complicated. So if you remember from our types of compounds video, bases are any cation, it can be a metal or a polyatomic, plus an hydroxide. So hydroxide is the polyatomic ion OH. Oh, just found a typo in those notes there. This is when writing the formula for an acid. It's because I copied and pasted. We are writing the formula for a base. You need to make sure ionic charges are balanced, just like we've been doing for ionic and acid, and that's because those electrons get transferred. Let's look at an example here. Magnesium and hydroxide. The ionic charge for magnesium is a +2, and for hydroxide it is a -1. Those are not balanced. There's more positive than there is negative. So we got to add on some more negatives to make everything equal. If you add one more hydroxide, that balances it out because you've got a +2 with magnesiums and a total of -2 for hydroxides. You used one magnesium in that, and you used 2 hydroxides. However, you can't just write OH2 because that means 1 oxygen and 2 hydrogens. What you have to do instead is use parentheses around your polyatomic ion. That says I'm keeping the OH together. It's a polyatomic ion. They got to stay grouped, but I've got 2 of that whole group. So anytime you use multiples of a polyatomic ion, remember you have to do parentheses. So I want you to try all of these that are down here. Don't know why they're numbered weirdly. It'll be fine. I'm formatting this kind of late at night. Y'all are like the guinea pigs before I give this to my in-person classes. Nevertheless, you can still try these examples. Note that the Roman numerals, once again, are for the charge of the transition metals. So go ahead and pause the video. Try to balance out all of these formulas. Also, this should be bases. Finding all the typos here. Okay, pause the video. Try to write out all of these formulas. And there you have it. That's all the answers. Hopefully you got them right. Hopefully you know how to balance by now. If you don't, go rewind the video, try to figure it out, or email your teacher. Moving on down to naming bases. Naming bases is so much easier than naming acids, and really it's the same rule as naming ionic compounds. First thing you do is write the name of the cation. Most of the time this is a metal. And you write the word hydroxide. I did forget to put in here, and I'll throw it in for the in-person kids. But if it is a transition metal, if it's a transition metal, you have to use the Roman numerals to indicate its charge. Use Roman numeral. All right, there you go. If it's a transition metal, use Roman numeral. Otherwise, you just write the name of the cation and hydroxide for hydroxide. Pretty simple. Look at this first one. It is magnesium as the cation, so you just write magnesium. Whoop, whoop. And then you write the word hydroxide, because this is not a transition metal. Magnesium hydroxide. Super easy, no changes. This is probably as easy of a rule as it gets. However, if it is a transition metal, which I didn't put any of on this list, make sure you use that Roman numeral like you already learned how to do. Go ahead, pause the video, try these examples, and I'll put the right answers down. And there are the answers. As always, if you have questions or you need some help, you are welcome to email your teacher or come to our office hours. I think Rigsby's are on Tuesday, Thursday. Mine are on Wednesday, Thursday. Not sure when Sharp's are, but it should be posted in his classroom. Thanks for watching and have a great day.